Hello everyone, my name is Jack Blair, and along with Nicholas Rising, Onur Gunduz, and Nicholas Bonanno, we make up the SmartSkeg development team. Over the course of the past year, we've created a product mounted to a crew shell that collects valuable data for rowers and coaches. To help you better understand our product, let me talk about the sport of crew. In crew, 8 rowers sit backwards in the boat and push forwards to move the boat in the forward direction. One member, known as the coxswain, yells commands to these rowers to basically control the steering of the boat as well as how strong the rowers are rowing. As you can see, it's important the rowers take coordinated strokes to make sure the boat moves in one fluid motion and has maximum efficiency. Because of this, there are 3 important metrics to collect about rowing boats. First of all, there's the stroke rate, which is basically how many strokes the rowers are taking per minute. Obviously, when the boat's taking more strokes per minute, it's moving faster than a boat taking less strokes per minute. Additionally, we want to know about the split of the boat, which is basically how fast the boat is moving over a certain distance. Traditionally, this is measured over 500 meters, and boats range from 1 minute 30 for 500 meters all the way up to 3 minutes for 500 meters depending on the speed of the boat. One final metric to know about is the set, which is basically how tippy the boat is. Generally, boats that tip less are more coordinated and can move faster. So this is an important metric for coaches and rowers to analyze after they row. Let's talk about current rowing equipment. Traditionally, teams and coxswains will have a device called a cox box, which shows them 2 important statistics about the rowers. These are the stroke rate and the split. Basically, these are large, heavy rubber devices that have several buttons as well as an old display that controls them. This is traditionally held by the coxswain in their lap as the rowers go on their row. Now let's talk about our solution, SmartSkeg. We also have control over the stroke rate as well as split, but also introduce new data in the set of how balanced the boat is. This allows us to generate new insights such as how good a certain combination of rowers is and relay this data back to the coaches. We also have data such as the timers and distance travel that the Coxbox has. Instead of using the display that the Coxbox uses, we display all information to a mobile phone that the coxswain is already carrying on their person. This means the phone is held by the coxswain in the stern of the boat, and our device, the SmartSkeg, is mounted on the bow or the front of the boat. Additionally, the Coxbox is incredibly expensive, some retailing over $1,000. There are other products NK Sports produces that range from $400 to $500 as well. Our product will retail for $300 and is currently $70 for us to produce. Over the course of this year, we've aimed for 3 major advancements over Coxbox technology. First of all is more advanced rowing statistics. Like I mentioned before, we capture set, split, and stroke rate, as well as data about which rowers were in the boat at any given time, so we can generate the best possible outcomes and lineups of rowers for the coaches. Additionally, we can stream data straight to the coach's phone, just like the coxswain's phone, using the same protocols that we already have created. In this way, the coach can monitor real data about the boat in real time as rowers are swapped in or swapped out, or during specific drills in the practice. Additionally, we aim to provide autonomous steering for the shell as part of our product suite. This is incredibly useful for rowers because in smaller boats where there are only 1 or 2 rowers, steering is pretty difficult to achieve since there's no coxswain. Basically, we can control the rudder by analyzing our current position over GPS and steer the boat to a waypoint mission set out by the coach before practice. Finally, we aim to provide a module at a much cheaper price than the Coxbox. Currently, high school teams are already spending their budgets on new boats and new oars. This provides little money left for the equipment that they need to use every single day like the Coxbox. By creating a cheaper alternative, coaches will be able to receive better data about their team, as well as be able to afford more data collection modules to make their overall team better. Now, let's discuss how we made these modules. To talk about our early development as well as PCB creation, let me hand you over to Nicholas Bonanno.
Hi, I'm Nick, and this is the PCB hardware for SmartSkeg. So first off, what is a PCB? It stands for printed circuit board, and it is a way of physically connecting devices together. So there are actual copper traces under the green that you can't see. So we have, on the initial one, we had a few different sensors. We had the TT, which was our main microcontroller that was running the whole operation. You have a GPS module. That was high precision one, so you could get location. You had a microphone that we were originally intending to use for synchronization using audio, but we would eventually drop that. And we have an accelerometer so that we can get the tilt of the boat and the real-time acceleration so that we can get stroke rate and other details like the related. The red thing here, that's the GPS. The blue one close up is a microphone as it looks like it. The blue one shortly behind it is the accelerometer. You have the camera to the right. That was for if we needed it, if we wanted to do any type of video recording or guidance of the boat so that it could actually see where it's going. And then the big board in the back is the microcontroller. Our next iteration PCB expanded upon what we were previously trying to do. So the top two pad locations those are ESP32s. Those are microcontrollers with wireless transceivers in them. They were intended to talk to the Rudder PCB and to talk to the phone that would be controlling the SmartSkeg. We also had the camera module now in something called an ESP cam, so an ESP32 as well, but with the camera module on it, and you can see that that's about where it says antenna on the board. We had a switching power supply, but what it really meant though is that we had an actual power supply on board and we could power this from a battery, which was managed by that BMS where the big pads are. It was a board that sat on there and that stopped it from getting damaged from misbalanced batteries. We would refine this board into the iteration you see here, which is essentially the optimal version of that board. It was a 4-layer design that was capable of high-speed signaling. It would have actually fit into our case. It probably would have had manufacturing issues in hindsight, and potential form factor issues as well. And our final board, as you can see, is much slimmed down. So we realized we could probably drop the TNC entirely, and with that we managed to drop everything but the ESP cam when it came to controller and transceiver hardware. So we just have the ESP cam at the bottom, you have the accelerometer at the top, and you have the GPS on the right where that little box is.
Alright, being able to collect data with the PCB is incredibly useful, but this would never stand up to the test of rainy practices and the current wear and tear that devices will encounter on the river every single day. To account for that, we've created a hard 3D printed shell that goes around the PCB and allows us to protect the device from the elements. Now I'll go over the process that we used to create this. We created early prototypes in the fall, using 3D printed filament, PLA, as well as suction cups to adhere to the boat. In these early designs, we included a spot for the camera so that we could record out the front of the boat, as well as a lot of room for a battery and circuit boards inside. One major downside to these designs were that the suction cups were losing suction over time, which means we could place it on the wall or boat, and after 10 or 15 minutes, it would just fall off, which obviously is not good enough for what we need. Additionally, as we modified our PCB, we realized that the device could be much smaller than we previously thought, which allowed us to move into our next design. In our second design cycle, we made a smaller module with a singular suction cup in the middle. In this design, we pinched down the edge of the suction cup while we pulled up the middle, creating a vacuum to adhere to the surface. This allowed for much better suction, up to several hours. This used a clip to tighten the suction cup down, which means that coaches and teams could place this device on the boat and suction it on with the clip. At this stage in the cycle, I was also concerned about how waterproof the module would be. So I added one O-ring on the outside of the device, which protected from water coming in from the sides. Additionally, since the suction cup mechanism is inherently open to the water by design, I added an interior O-ring. Now, there's a donut shape for the electronics and PCB to be safely contained while the device is in operation. As we reached the final iteration of our design, we included several improvements that helped the design become much more usable for the average consumer. Because we wanted to include wireless charging, we opted for a non-circular Millennium Falcon-esque design. This also gave the user intuition as to which direction to point the module when attaching it to the boat. From here, we added the other elements such as the button, the screw-on cap to tighten the suction cup, as well as 2 embedded LEDs in the back to provide visible indicators for the rowers and coaches. As you can see from these pictures, the hardware has maintained very well. In just the past 4 days of practice, we've achieved 10 hours of on-water time with no issues whatsoever. The suction cup holds up very well, and the device is durable and strong for the entire practice. Also, the LEDs are bright enough to view in the daylight, so all the issues around this are solved. I also wanted to highlight the suction cup mechanism of this module in the final design. As you can see from this graphic, in this case, the surface of a boat is a laminate, non-porous surface that can adhere well to the suction cup. We also use a cap to pull the suction cup up. As you can see, there's an embedded nut inside of it that, as turned, forces the bolt of the suction cup to be pulled upward, creating the vacuum. Finally, we wanted to include wireless charging on this design to keep the device fully encapsulated and away from the elements. We were able to do this, as well as incorporate the tolerances needed to accommodate this charge. Now, allow me to go in depth about our firmware stack on this device. To begin, we chose the ESP32 microcontroller for this project, mainly because it had Wi-Fi and Bluetooth capabilities. Essentially, it is a faster and more efficient Arduino. The final configuration we found was one that had an SD card as well as a camera, known as the ESP32 cam. All of these are developed by Espressive Systems in Shanghai, China. To upload and run code on this device, we used the development framework Platform.io. This was coded in VS Code using the Platform.io extension. Traditionally, Arduino sketches have a setup and loop function. The setup function is called once to begin the processes, and then the loop function is called forever until the device is turned off. For example, if we have a blinking LED, we'd include the initialize LED in the setup function, and then the turn on, wait, turn off in the loop function. This would make the LED flash forever. However, this would not work for our device, since we need to maintain multiple asynchronous connections as well as collect data at regular intervals. Because of this, we used a state machine setup. This allows us to define multiple states and use different loop functions inside of each of these states. The most basic state is the booting up state, where we initialize all of our sensors, as well as the SD card, and make sure everything is functioning properly. Then, we move to the idle state, where we wait for the user to connect on their phone. In this process, we use minimal current by only creating our web server and not turning on any other sensors. From here, when queued by the phone, we move into the recording state. We launch additional subdirectories such as GPS and Excel to post our new data to them, and we also start collecting our live readings. On the SD card, we create a new file directory for our current session, and then start propagating files with our new data. We record GPS data every second, and record accelerometer data 20 times a second. We then store each of these to a custom database and update the LEDs to reflect any current changes. When the user wants, we can move back to the idle state by clicking the End Session button on the phone. Then we can do one of two things. If they want to check the files after practice, they can go into the filing state. From here, we will generate CSV files of all the data and send it to their computer for post-analyzation. One cool feature that we have is an over-the-air update. We included this because we want the device to be self-contained. Traditionally, microcontrollers must be updated using a flasher device such as this. But with an over-the-air update, we can do this all asynchronously. In the OTA update state, we turn off all of our sensors, make sure we're in a safe memory mode, and wait to be queued from the phone. From here, we receive the new bin file, upload it into Flash, make sure it's valid to run, and then boot into the new firmware. You can see the arrow going from the OTA update state straight into the boot process because as we get our new software, we reboot into this new system. We've completed many OTA updates in this development process, which means that in the field, we can update the software whenever we want using Wi-Fi. This actually is a huge deal because in the future, when this device is on many crew boats all around the nation, we can send out bug fixes or patches to any device across the nation.
So now on to the mobile app. But before I run through the mobile app itself, I'm going to quickly talk about how the BAL module communicates with the app and any other peripherals. There are several ways to send data to and from an ESP32, such as the one we have on the BAL module, and you've probably heard of a few of these methods, most likely TCP, UDP, and HTTP, to name a few. Each of these are protocols in the Internet Protocol Suite, but as you can probably tell from this slide, we settled on HTTP or Hypertext Transfer Protocol for our communications due to its relative simplicity to use, along with our familiarity with mobile and web applications that generally involve HTTP. To initiate the communication between a device and the BAL module, you simply have to connect over Wi-Fi. Looking at this slide, you can see the important snippets of the code that handle this communication stream, but it can be easier abstracted to something like this. Now that you're connected over Wi-Fi, the BAL module is basically acting as a router, while any peripherals such as the coxswain's phone or the rudder are connected to it like you'd connect to your Wi-Fi at home. Now let's say that there's some data the app wants, such as speed of the BAL module, so we can calculate our split and tell the rowers how fast they're going. On the left side of the diagram, you can see how the app makes the HTTP request, and it's much like visiting a website in your own browser. You may even recognize some of these numbers because much like how your router at home is most likely accessed on the private IP 192.168.0.1, the bound module's ESP will always be 192.168.4.1. Tacking onto those numbers, it specifically makes a request to the subdomain GPS. In response, the bound module receives this request, finds the last GPS data point is taken as stored on the SD card, and returns it in a conveniently packaged JSON or JavaScript object notation used to turn plain text into nicely packaged information. The app then asynchronously receives this JSON and can parse it however it wants to get the data it wants for any purpose it needs. Likewise, let's say you need to have a slider on the app and you want to control a rudder that's also connected to the ESP32 on the bound module. In the previous example, we sent data from the bound module to the phone, but in this scenario, we also need to send data from the bound module to the rudder. We also need to send data from the phone to the bound module. For this, we can use HTTP GET requests. So much like a Google search, where in your URL you're going to have a little question mark along with what you're actually searching for, you can use these query strings in our HTTP to send information from the client to the server. In this scenario, the user moves a slider, say to angle 50, and the app then makes a request to this URL 192.168.4.1/rudder/control. And then it also tacks on the query dest angle and sets it to 50. The bound module then receives this request and stores it in memory. Meanwhile, the rudder is making requests to 192.168.4.1/rudder/dest angle, and it's making this say 10 times a second. When it makes this request after the user has now moved the slider, the dest angle has changed, and the bound module can return that JSON like it normally would, but now it reflects this change, and the rudder knows that it needs to now turn to 50 degrees. Now, onto the actual app. The SmartSkeg Coxswain app had several primary goals in mind from its inception, namely ergonomics and application of data. In the way of ergonomics, a major emphasis was the modularity you see on the screen, and you can see how everything is nicely spaced compartments and containers and all that kind of stuff to make it as readable as possible to the user. The other goal, application of data, is reflected by the various numbers and particularly the graphs you see on the screen. We know that we had the means to collect a lot of data that simply had not been looked at before in this kind of context, at least outside of specific studies on the kinematics of rowing. So we wanted to put that to use. Unlike the commonly used Cox boxes, the Coxswain with our app is able to see data in real time. Just to run through the various features on the app, going down the diagram, you can see split, or the current pace you're going, represented by time to go 500 meters. Stroke rate, or the rate that strokes are being taken at in strokes per minute, a timer allowing the coxswain to measure specific pieces on the coach's command, and a rudder control slider using the aforementioned HTTP communication link to send commands to a rudder. On the right of the diagram, you can also see several more features. As represented by the notched arrow, by holding down any of the components, the coxswain can quickly read a tooltip about its use. To the right of the stroke rate, you can see an acceleration curve, allowing the coxswain to visualize the stroke rate, or allow them to visualize the acceleration of the boat over the course of the stroke, and potentially identify any issues with that. And then finally, below that, you can see where the modularity of the app is really highlighted, where with a simple swipe of the application on the timer, the coxswain can scroll through several modules. In this case, we have the timer and a set graph. And with the set graph, the coxswain can look at the keel of the boat over the last several strokes and possibly identify a pattern with the way the boat is tipping, hopefully to identify issues with a certain part of the stroke.
Now, let's head over to Onur Gunduz to talk about the desktop app.
As a companion to our SmartSkeg Coxswain app, we offer the SmartSkeg Workout Analyzer app. This desktop-sized SmartSkeg app is geared toward athletes and coaches who would like to review their performance after practice in order to identify problem areas to target, as well as to optimize boat lineups. The user inserts their SD card, picks a particular day of practice from a full-screen menu, and the app fetches the appropriate CSV file from the proper directory to interpret data from. Then, the app utilizes Mapbox's wonderful array of GIS options to build the most helpful app for the situation, identified by the user in a drop-down menu. For example, if the user wanted to put the row into context regarding weather conditions, they would select two options. First, the wind option to see how much the tailwind helped or the crosswind or headwind hurt throughout the row, and two, the speed option to see if the velocity to see the velocity graph throughout the row in a color gradient of their choosing. The app also allows for the user to scale how prominently the data should be displayed using a slider that adjusts to any level of granularity, from an average of the entire row to each individual data point. Just like the mobile side of the app, the desktop app was built with Google's Flutter, which uses the programming language Dart. The plentiful nature of Dart's documentation and its open source philosophy regarding packages where anyone can upload their work made it a pleasure to use. Libraries that were especially helpful were lat-long for storing location data, FlutterMap for communicating with our map API, Mapbox, and to display the map, and some path provider and management libraries for selecting and retrieving the CSV data. Initially tested on the web with Chromium, the desktop app uses Flutter to now support the Linux desktop, Windows desktop, and Mac platform as well. The consistent use of Flutter opens the door for the after workout mapping side of the app to one day actually get integrated with the main rudder control and live visualization parts.
Now, let's talk about how coxswains steer the boat today. To steer the boat today, coxswains turn the rudder using a circular rope that loops around themselves. This rope has 2 knots attached to it, and by pulling this rope forward or backward with both of their hands, they can steer the rudder. For example, to turn right, the coxswain would push the rope forward with their right hand and pull back with their left. This would spin the rudder out to the right and turn the boat to the right. The issue with this design is that the coxswain must always be applying force to this rope to turn the boat. And additionally, this makes the coxswain have to manage 2 things, controlling the rowers and steering the boat at the same time. In smaller boats that don't have coxswains, like singles, doubles, and some fours, rowers must steer by looking behind themselves and then steering with their foot. This is time-consuming, annoying, and can distract the effort a rower can put into their piece during a rowing workout. To solve this issue, we have created a rudder module that can connect wirelessly to our bow module. As you can see from this design, this mockup is 3D printed. We use an angular servo motor, basically a motor that can turn to and maintain a certain angle given an electrical input. Ours has up to 20 kilograms of force that can be supplied to it, which is more than adequate enough to steer the boat. To supply this pulse width modulation signal to the servo motor, we need another CPU on this module. To manage all the circuitry, we made another PCB. There are 3 main things on this board. First of all, there's another ESP32 module. This allows us to control the servo over PWM, as well as connect to our bow module over Wi-Fi. We also have a battery regulator circuit in blue, which controls the voltage of the battery, and a regulator down to 5 volts for the ESP32 as well as the servo motor in red. One challenge we faced was that since we needed 5 volts for the servo instead of 3.3 volts like we did for the bow module, we needed a 2-cell LiPo. This means that since each cell in the LiPo contains 3.7 volts, this new battery would have 7.4 volts for us to work with. The challenge was that now that our voltage was higher than we needed to regulate it down to the new level. So we included an onboard linear regulator, and like you can see in blue. To turn on our module, all we need to do is plug in the battery, like so. Now you can see we've powered the circuit. To control the rudder, all we do is plug in the servo cable into our board, like this. Like you just witnessed, our rudder snaps into place in case of any power failure or any loss of signal. This is because if we're maintained at a certain angle and we lose connection to our bow module, we don't want to immediately continue at this angle. We want to revert to an original angle and then let the coxswain take over from there. The firmware of the rudder is quite simple. We basically repeatedly check the bow module to see if there's any update in our input state. For example, every 20 milliseconds, we'll send a new request to the web server on the bow module. If its current angle has been changed, we reflect that change by turning our servo to that angle. Since there's not always a guarantee that our current angle will match our designated angle that the bow module wants us to move to, we report back our current angle as we continually progress to the destination angle. We also implement a PID controller, which stands for Partial Integral Derivative Controller. Essentially, this allows for a smooth interpolation between any 2 points. If we're at a current angle and want to move back to our original angle, we can smoothly transition to that point, which makes the steering of the boat much nicer for the rowers. In the future, the form factor of this rudder will be much smaller and will fit inside the stern of the boat. Let's talk about some lessons learned throughout this year. We've learned it's best to put as much time as possible in the middle of the year. This is because you have the least assignments due at this point and you have the most time to sink into your project. Additionally, we recommend getting all the hardware deadlines done first and rushing software at the end. This is because hardware must be ordered, assembled, built, and refined, but software can be coded and refined really quickly in the last few weeks. In the last few months of the year, we had to get rid of our previously created design and opt for a more elegant, simple, and cheaper design that we could mass produce. This allowed us to have a better overall product and was just part of the process that it took us to get to this point. In the example below, we've shown an optimal work year for a senior research project. As you can see, work begins over the summer, declines during college app season, and then immediately increases over the middle of the year and into spring break. Of course, at the final push, you're putting in the most work into your project. As far as future advice, we'd like to warn you, do not be afraid to change projects. We had 2 of our group members join us in January, and because it was something they enjoyed working on, we were able to get a lot more work done in general and have a more fun final project. Additionally, working in a group is a good way to motivate yourself to get more work done. Perhaps most importantly, work on something that you want to do. In this case, since most of us were on the crew team, creating a crew-oriented project was a super fun choice because we were able to test devices on the water almost daily. One very important lesson we learned is that sunken cost fallacy, the idea of spending so much time on a design that you can't move away from it to a simpler design, is not the right idea. We learned that by treating our previous designs as learning points, we are able to optimize and create the best design throughout the process. Don't get stuck on old designs you put so much time into that you can't move on from. Finally, there is nothing more permanent than a temporary solution. We found that our very first PCB designs were able to record more on-water data than our newest ones. This is because the very first design has the most time to be implemented and tested in the field without you worrying about it getting damaged or broken, since you already have new iterations ready to go. Of course, we'd like to say a huge thanks to Mrs. Cusco, our Robotics and Automation Lab Director, for helping us in every stage of this project. We'd also like to thank Mr. Gordon, Mrs. An, Dr. Yilmaz, and Mr. Kosek for every piece of help that they gave us throughout this journey. Thank you to the TJ Robotics and Automation Lab for running this project. Additionally, thank you to TJ Crew for allowing us to test and implement our modules on the water every day in practice. We'd like to thank the open source community for allowing us to build this project using tools available to the entire internet. And we'd like to especially thank Daniel DeConti, Ari Bobesh, and Simba for all the help they've given us on particular issues. Thank you for everyone who's helped us along the way.